Today I will go through some problems on the application of integral calculus. So let's start with area bounded. This is example 1. So you want to find the area formed between this curve and the x-axis. So usually you need to work out whether the curve is above or below the x-axis. You can test by looking at the domain. So you look at each of them separately. So for x minus 1, if x is between 1 and 2, hopefully you can see that x minus 1 is greater than or equal to 0. Similarly, for x between 1 and 2, 2 minus x is also greater than or equal to 0. So you multiply two things which are greater than or equal to 0. So you will end up with something greater than or equal to 0. So in this case here, you can just go ahead and integrate it. And with the method of integration, so obviously it's not partial fraction. So you either use substitution or you use integration by parts. So normally substitution is easier if it works. So in this case, if you let 2 minus x to be u and then find the u dx, which turned out to be a constant. So the x is just equal negative the u. So what you've done is, in this case, instead of having root of two things inside, you end up with only u power half. And then for x minus 1, so if you just make the x, if you make x the subject here and then substitute in, you have 1 minus u. So comparing this to that, so this one you can expand out and then integrate. Next problem is on related rate of change. So in this case here you got a curve, and if you rotate that curve around the y-axis, you will form basically a volume. So we need to show that a volume is given by this, where h is the height. So imagine you have your height over here. So if you rotate this curve about the y-axis, remember the formula is this. You want x squared to be inside because x squared is like the radius when you rotate. And you want to integrate from 0 to h with respect to y. So x squared, you go back to here. You need to make x squared the subject first. And then you can integrate that now. So next part, they give you the V dt, basically cubic meters per second. And you need to work out the h dt. So they ask you to show that the h dt is given by this. So firstly, you need to work out the V dh because you got V here already in terms of h. So you find the V dh. And then to work out the h dt, you use your product rule here. So you basically substitute in. Alright, now, so next we look at the volume of revolution. So you got this curve and this line, and then you rotate them by 360 degrees about the x-axis. So you want to know what the expression is to work out that volume. Think of it like this. So if you got two different functions, so you want to take the volume further away from the x-axis minus the volume closer to the x-axis. So you need to work out a point of intersection in this case here. So just make the two equal to each other. So for x, you can do that on CAS. And then to work out volume, so this one is further away from the axis, the x-axis. So we call that y1. And this one is closer to the x-axis, you call that y2. And then you just substitute in. So y is that, so y squared going to be this. And then your y2 is just the horizontal line. So substitute in. So now this time I can separate the two terms out. because this one is just a constant. So I can just go ahead and write that will become just x, and you sub in your limits here. So now this part here just remain. You don't need to write that. And the answer is just day. Just a note on this one here, because you have a horizontal line. So when you rotate, you will generate a cylinder. So another way is this, you can just iterate this bit here and then use the formula for volume of the cylinder to get this part here. So today I will not go to surface area and line of curve, but you guys need to go back and revise. So for surface area, make sure that you know the formula about the x-axis, about the y-axis. So both for Cartesian form and parametric forms.